Okay, so we are just wrapping up some stuff up from this section on the chain rule. So here, this is part 2 of this section 3.4. And so I've copied down the chain rule so you can reference it. It's right here. If you're not taking notes on the PDF, then probably you don't need to copy this whole thing down because it's just, you have it on your other notes. Okay, so one thing I wanted to show you was that we can derive the quotient rule by using the product and the chain rules. So what I mean by that is, remember the quotient rule tells us how to take the derivative of f over g. So if we have a ratio of two functions, and what we can do is just rewrite this as f times g to the minus 1. So I'm writing it with a negative exponent so I can bring it up here. So note that I wrote the minus 1 out here, so this is not g inverse. So hopefully just note that this is not equal to this. This is 1 over g. Right? Okay. Okay, so once I do this, I can use the product rule because I have a product of two functions, and I would get the derivative of f times g to the minus 1 plus, f times, g, or the derivative of g to the minus 1. Okay. So I'm going to leave that like this because this is the part that we have to use the chain rule on, because we have our outside function is x to the minus 1 and then our inside function is g. So in this first part I can turn this back into a fraction by pulling the g to the bottom again, so rewriting this as f prime of x over g of x. And then in the second part, I'm going to actually compute this derivative. So this would be, first we use the power rule. So that would be negative g of x to the minus 2. Minus 2. And then we multiply that by the derivative of the inside function, but that's just g prime of x. Okay. So, if we just simplify, we get this. That negative will come out front, and we'll get f of x times g prime of x over g of x squared. And then if we want to combine these into one fraction, we just find the common denominator, and so we would need another copy of g of x in the first fraction. So multiplying top and bottom by g of x, we would get f prime of x times g of x minus f of x times g prime of x over g of x squared. Okay. So you can see that what this means is that really quotient rule is just a combination of the product and chain rules. The thing that is nice about quotient rule is you notice that we did all of this simplification and combination, and at the end we got this one big fraction. So what happens when you use quotient rule is it's doing that work for you. So you don't have to do every time the chain rule and then combining it to make one fraction. So it's convenient, and that's why we use it a lot. Okay, so a little bit about why this is called the chain rule. So product and quotient rule, it's kind of obvious why they're called that. The chain rule is not so obvious, but when we look at differentiating compositions of 3 or more functions, let's see what would happen. So we would say we have a function that is f composed with g composed with h. Right, so this is a composition of 3 functions. and we want to take the derivative. So first we could write this as f of g composed with h, and treat f like our outside function, and our inside function is g composed with h. Right, so that whole thing, and then outside would just be f. And we can use the chain rule. So f prime would be f prime of g of h of x, and we would multiply that by the derivative of g of h of x. Okay. So we want to take the derivative of this composition of functions. Now there's only two of them, so we treat it like we normally do with chain rule. So our outside function is g, inside function is h, so outside function is g, right? And then we just take the derivative again using the chain rule. So I leave this first part alone, right? And then I'll get, so I have the outside function evaluated at the inside function times the derivative of the inside function. Okay, so see that when we had a composition of three functions, we get three derivatives like this, right? So we have three pieces. And so it's actually nicer to see in Leibniz notation, then it's really clear. So if I label my f, I'll call this f of u, and then u is g of x, and then x is h of t. Then if I want the derivative of y with respect to t, that would be dy du times du dx times dx dt, right? So then you can really see that there's really just three derivatives being multiplied together. And then if you were to have a composition of four functions, you would get four pieces. So the longer or the more functions you have composed together, the more derivatives you get in this chain. And then, so that's why it's called the chain rule, because you add another, so you compose with a new function, and then it adds one more derivative to the chain, right? Okay, so I think I'll stop here, and the next video will just be a few more examples.